to kind of illustrate the difference between some things that we're going to be using, some terms we're going to be using. This will kind of review what we've done so far regarding velocity and hopefully teach you something new. So I would take some notes during this so that you don't have to keep referring back to the video all the time. Excuse me. So far, here's kind of where we're at with velocity. We've sort of figured out that the slope of a position versus time graph, it kind of tells you two things. It tells you, first off, what way an object is going. Is it going in the positive or negative direction? And it also tells you how fast it is going. So it tells you both speed and direction. So velocity, if you will, is first, how fast, and secondly, and which way an object is going. So we typically say that the positive direction is to the right, and we typically say that the negative direction is to the left, because we've only really done horizontal motion so far. Later in the year we'll kind of expand this idea to, maybe positive could mean up and negative could mean down, but at this point we're just talking about things that move back and forth along a line. The speed is actually kind of shown by the steepness of the graph. So we can, it's not strange as this sounds, say that steepness equals fastness. Put that in quotes, technical term there. So the steeper you see a position versus time graph, the faster the object is moving. If the graph has a positive slope, that means the object's moving to the right in the positive direction. If the graph has a negative slope, that means the object is moving to the left. That's basically what we've done with velocity so far. Now, two terms that we have to kind of discuss, because we have to differentiate between them now, are average velocity and instantaneous velocity. Now, average velocity is literally over a given time interval, on average, how fast was an object going in what way. That's literally what that means. And here's the kicker. It is over an interval of time. Intervals of time have beginnings and endings, so I'm talking about a period of time. Now, average velocity we have defined, by the way, there are a couple of symbols that you can use. You can either say VAV, or you can do a V with a little line over it. Both of those mean average velocity, and I'll kind of use them interchangeably. Here's a problem with physics that you're going to see everywhere is that there's a million ways to say everything. Nothing seems to be terribly standardized, so you're going to see lots of symbols. I have no way around that. We earlier defined velocity as the slope of a position versus time graph, so if we want to talk about average velocity, what we're going to say is V average equals how far it has gone. Now this is its displacement. So how far it's gone divided by the time interval. So this is the object's change in position divided by the time over which that took. So this is kind of a big equation. Average velocity equals displacement over time. Remember, whenever you find changes, you have to find them in the correct way. So if you're going to find the change in position, you're going to do the position later minus the position before. Same thing with time. The time later minus the time before. Make sure you find your changes in the correct order all the time. Now, instantaneous velocity is, okay, just at one point in time, how fast and what way is the thing going? Now, that gets a little bit trickier when you're talking about things that change how fast they're moving, but for right now, I want you to see that for any kind of motion like this, like we kind of started out the year looking at, the average velocity of the object and its instantaneous velocity aren't any different. Let me illustrate. Let's say that I wanted to find the average velocity of this object This is just an object that's moving at a steady kind of clip, maybe moving to the right. Maybe this is like a air hockey puck, just drifting very, very steadily. I guess this would be a long table though, because this is like 20 meters. So let's say I wanted to find this thing's average velocity. I would have to find the change in position divided by the change in time. Well, my change in position here, if I wanted to find the average velocity over the first 6 seconds, would be change in position. That would be 18 meters minus 0 meters. That's the change in position, divided by the change in time, which would be 6 seconds minus 0 seconds. So for this motion right here, my average velocity would be we said 18 meters minus 0 meters over 6 seconds minus 0 seconds. That is 18 divided by 6, or 3 meters per second. Now that's on average the velocity of this thing over the first 6 seconds. If we want to talk about the instantaneous velocity, that's how fast something is moving at just one moment in time. Well, that's really easy to do in this case. Here's why. This thing did not change the way it moved throughout the whole 6-second interval. So not only did it have an average velocity of 3 meters per second over the 6-second interval, its velocity at any moment in time, whether it's on one of these second marks or not, is also 3 meters per second. Its instantaneous velocity is the same as its average velocity. And that's really easy to see with something that's moving steadily like this. The trick comes in when objects don't move steadily. So for instance, what if an object is behaving sort of like the dry ice puck in the experiment that you just did? Well, then things get a little spicier, I guess you could say. That last object was moving steadily. This object, not so much. This is actually a basketball that was rolling down a sloped driveway. So here's its motion map. At a time of 0, the object was at a position of 0. At 1 second, it was at about a half a meter. At a time of 2 seconds, it was at the 2 meter mark. At 3 seconds, it was at the 4.5 meter mark. At 4 seconds, it was at the 8 meter mark. At 5 seconds, it was at the 12.5 meter mark. And at 6 seconds, it was at the 18 meter mark. So this is a motion map. And these are velocity vectors. They represent how fast and what way it was moving. Longer arrows mean faster motion. So plotting this on a position versus time graph, it doesn't give you a line, it gives you a top opening parabola, at least half of a top opening parabola. So now let's look back at what's going on here. We could figure out the average velocity of this thing over the 6-second interval. And let's go ahead and do that. The average is change in position over change in time. The change in position is 18 minus 0 meters, so 18 meters. The change in time is 6 minus 0 seconds. 6 seconds equals 3 meters per second. Now here's the weird thing. If you paid attention, that is the exact same average velocity we saw with this motion. But this is a very different motion. So it's true. On average, both of these things went 18 meters in 6 seconds, so they have the same average velocity. But this object here started off at rest and ended the 6 seconds going much faster. So it might have had an average velocity of 3 meters per second, but that doesn't mean that it was going 3 meters per second the whole time. This thing started off, let's look at the slope, started off at rest, and every second that went by, the thing had gone faster and faster and faster. By the time it hits 6 seconds, the thing is going quite fast. The graph is really steep. So let's look at what it means to have the instantaneous velocity here. Instantaneous velocity is kind of weird because it's an object's velocity at one moment in time. There's no way we can use this same equation to figure out instantaneous velocity, simply because if we're talking about one moment in time, the change in time would be equal to 0, and you can't divide by 0. So this equation is not going to work for us, but clearly, this object has a certain velocity at all of these times. It's just this equation doesn't let us find them. Now, if you're splitting hairs, you would actually have to use a branch of math called calculus to figure out this object's instantaneous velocity. But since this isn't a calculus-based physics course, here's how we're going to do that. We're going to do a really, really good approximation of it, and it's going to be algebraic. So if I want to know the instantaneous velocity, let's say at 3 seconds. So notice I'm not putting a line over it. Let's say I want to know exactly how fast this thing was going at a time of 3 seconds. Here's a way to do that. Remember that velocity is the slope of this graph. I could simply take a ruler and do my very, very best to approximate the slope of the graph at 3 seconds. Here's what I've done here. Now you can probably see that line I scratched in there real lightly. It's actually called a tangent line. You probably remember from geometry, a tangent to a circle is a line that touches the circle at only one point, but never actually crosses over the circle. Well, same idea here. This is a line that doesn't really cross through my curve, but approximates the slope of my curve at that time, 3 seconds. So it's tangent. Well, if I were to find the slope of this tangent line that I just drew, that would represent the instantaneous velocity of the object at that time. Now, finding the slope of a line is pretty easy stuff. All you have to do is pick a couple of points that actually sit on the line, do your slope formula, figure out the rise in meters, figure out the run in seconds, and divide them. But here's a shortcut, because that would mean I would have to read new points off my graph, and I would have to draw in this line, and it's kind of a pain. Here's a nice shortcut to figure out the instantaneous velocity at a given time, like 3 seconds. If I look at the interval of time from directly before to directly after the time I'm interested in. So if I want to get my instantaneous velocity at 3 seconds, I'm going to look at the time interval from 2 to 4 seconds, because it's from right before to right after. And here's what I'm going to do. I'm going to draw a little line segment from 2 to 4 seconds. Now, if you compare this segment I've drawn with the tangent line that I drew, you're going to see that they're parallel. Meaning, instead of drawing in this tangent line, all I really have to do is imagine I've drawn a line from 2 to 4 seconds, and then I can find the slope of that line, because the slope of this little segment is going to be equal to the slope of my tangent line, and that will be my instantaneous velocity at 3 seconds. So my velocity at 3 seconds would be the slope of that line segment that I've drawn. So I'm going to look from 2 to 4 seconds. So my displacement from 2 to 4 seconds looks like it's at 2 seconds. I was at 2 meters. At 4 seconds, I was at 8. So 8 meters minus 2 meters, that is a 6 meter displacement. And it's positive 6. And from 2 seconds to 4 seconds, that is a 2-second change in time. So at 3 seconds, my instantaneous velocity is 3 meters per second. I could do this for any time on here that I wanted. Well, almost any time, as you'll see. I could figure out my instantaneous velocity at 4 seconds. Let's try that again. So if I want to know my instantaneous velocity at a time of 4 seconds right here, I'm going to probably look at the interval from 3 to 5 seconds. So right before to right after. And I'm going to do this, change in position over change in time from 3 to 5 seconds. So my change in position from 3 to 5 is going to be 12.5 minus 4.5. That's my change in position. So 12.5 minus 4.5, which is 8. And that is happening in a time of 5 minus 3, 2 seconds. That means at 4 seconds, my instantaneous velocity is 4 meters per second. I could do this at 2 seconds. If I'm going to do this at 2 seconds, I'm going to look at the short interval of time from 1 to 3 seconds. Use the same equation though. So from 1 to 3 seconds, that's a displacement of 0.5 to 4.5. That'd be 4 meters positive. And that's happening again over a 2-second interval, because I'm looking at 1 second before and 1 second after. So I get plus 2 meters per second. I want you to see what this means. At 2 seconds, this thing had an instantaneous velocity of 2 meters per second. So at this time right here, the thing was going 2 meters per second. At 3 seconds, it was going 3 meters per second. It had sped up. At 4 seconds, it's going 4 meters per second. It had sped up. And you can see the graph is getting steeper and steeper as time goes on. Now, I had said earlier, kind of mistakenly, I guess, that you could do this for any time you wanted on the graph. Here are a couple of times that I can't do this for. I can't do it here, and I can't do it here, simply because I don't have anything before to go with my after point. Same thing here. I don't have an after point to go with my before. So if you use this method of approximating the instantaneous velocity at a given time, understand you won't be able to do this at your first and last point. Another interesting thing to point out here, when we did the average velocity over the full 6 seconds, it ended up being 3 meters per second. Well, right in the middle of that interval, at 3 seconds, it's going 3 meters per second. So this is an object, this was a basketball rolling down a long driveway maybe, something like that. This is an object that began at rest and ended up going a certain speed, but right in the middle, its instantaneous velocity was the exact same as its average. And that'll become more important later on.